So I'd like to talk on modeling irregular solar cycles using flux transfer dynamo model. So the layout of my talk is like this. So first I will give a brief overview of the observation evidence of solar cycle and its irregularities, and then I will use flux transfer dynamo model to explain this irregular solar cycle. So these are the reference. So in 1609, Galileo invented his telescope, and after the invention of telescope, people started counting sunspot number regularly. So this is the sunspot number series from 1609 to present. So you can see that after few years of this invention, the sunspot number almost disappeared for several years, and this period is known as Monday minimum. So it was reported that the period of Monday minimum was from 1645 to 1715. Hoyt and Sartain reported that it was not an artifact of few observation but a real phenomenon, because they reported that 68% of the days were observed during Monday minimum, and sunspot appear only during 2% of the days. One important feature of the Monday minimum is the north-south asymmetry, which was there during the last phase of the Monday minimum. And so here I show the butterfly diagram from their paper, and so you can see that the most of the sunspot appear in the southern hemisphere. Okay. So there is a strong north-south asymmetry during the last phase of the Monday minimum. And another important features of Monday minimum was studied from the cosmogenic isotope like beryllium-10 in polar ice cap by D. Riddle. So they reported that although the sunspot were disappeared during Monday minimum, but the cyclic oscillation of the solar cycle were going on during Monday minimum. So this is the cyclic oscillation found in beryllium-10 data. I can see that actually the solar cycle was going on during Monday minimum. And the same results were found from another cosmogenic isotope, carbon-14 data. However, they reported that the solar cycle period was a little longer than 11 years. Okay. So this figure is taken from their paper. So they are suggesting that the dominant period during Monday minimum was around 14.4 years. Okay. From the same cosmogenic isotope data, carbon-14, Ususki reported that there were 27 grand minimum in last 11,000 years, okay, with a different duration. So this histogram shows that the number of grand minimum with different duration. However, after Monday minimum, you can see that the sunspot number more or less varies cyclically with an average period of 11 years. However, the individual cycle amplitude and also the period vary randomly, cycle to cycle. However, if you see this figure closely, then you can see that the stronger cycles are having shorter rise time. I mean, they rise fastly, and however, for weaker cycle, the rise time is longer. So if you zoom this plot, then you can see clearly that these weaker cycles are having longer rise time, whereas for stronger cycle are having shorter rise time. So this effect is known as Waldmeyer effect. So basically it says that there is an inverse correlation between the rise time and the cycle amplitude. By cycle amplitude, I mean the peak value of the sunspot number or the strength of a cycle. Okay. However, recently Dick-Portigal claimed that the Waldmeyer effect does not exist in sunspot area data. Okay. So basically they calculated the rise time as the time difference between the time of the solar minimum and the time of the solar maximum. Okay. However, we studied the Waldmeyer effect in the following way. So first we calculated the rise time in the following way. So let's tease the peak value of a cycle. Okay. Then my rise time will be the time taken during which the solar activity changes from point 2p to point 8p. Okay. So this will be my rise time. So calculating rise time in this way, we find an anticorrelation between the peak sunspot number or the P and the rise time, both for sunspot number and for sunspot area. So we call this anticorrelation between sunspot number, between rise time and the peak sunspot number as WE1. Yes.
Sorry. These dots are the actual data.
These are just the straight line fitted. This is the base fit. These are the actual data. Yeah. So we are using last data from last 12 cycle.
And you are saying there is a correlation.
There is a weak anti-correlation. This is what we found. So we are calling this as W1, and the next will be interesting. Like if we consider instead of rise time, if we do not consider rise time, let us consider the rise rate. By rise rate we mean the slope between 2 points at a separation of 1 year, with the first point 1 year after the solar minimum. Okay. So my rise time, rise rate is the this n2 minus n1. So basically this is the slope. Now calculating rise rate in this way, we find a very strong correlation between the rise rate and the peak transport number, both for transport number and for transport area. Okay. So we call this positive correlation between the rise rate and the peak transport number as WE2. So by what am I written? Yeah.
You change the 1 year to something like 2 years.
Yeah, I have very So and
it kind of remains the same.
Yeah, almost same. It is a very robust features of the solar cycle. However, if we just consider the rise time, the total time what I shown earlier, this is there is a correlation, but I don't know how strong. With last 12 cycle data, we cannot talk about significance level or other things. So we just point out there is a weak correlation. So this is W1 we are calling, but instead of rise time, we just consider the rise rate or the steepness or the how fast it is rising.
Only 1 year then.
Sorry?
Only 1 year of rising.
Only 1 year of
Rising sunspot number.
For the rate, you use only 1 year.
1 year. No, you say per year.
This we can take, like instead of 1 year we can like say 2 years, then my rise rate will be n2 minus n1 divided by 2. So that and we have actually calculated the rise rate in different region, like here. We have checked that this is the robust correlation.
And the previous one is what? So the for this
this is rise time. Basically, this is we are considering this. Like sometimes the solar minimum is not sharp. Like it is very difficult to identify where is the minimum. So therefore, we just remove this minimum and we go little beyond this minimum. So basically, my rise time is this 0.2 P to 0.8 P.
What's the ordinate here? The y-axis?
This is transport number.
Transport number.
This is transport number. So first we can find out.
number is the maximum, yeah?
No.
That was P.
This let's say is 80.
Oh yeah.
So we just find out first what is the peak transport number, and then we find the corresponding time where the transport number is 80% and 20% to 80% changes.
But is this correlation physical, or it's just because you have a fixed period? So if you have a sharper rise, you are going to have a larger number of sunspots, no matter what.
Yeah, if cycle is stronger, like if we see, so you can see these are the stronger cycle. So you can see that the rise time is shorter. It rises very sharply.
But I don't understand. Is it really physics? If I take any points and I put it up, the rise time will become.
You're basically saying that it doesn't depend on the whatever dynamics you choose.
Yes, it doesn't depend on the
Basically
dynamics.
kinematic.
Well, in a certain sense, yes. If you have a triangle and you put up the vertex, you will get steeper. But there's no physics in that. It's just how triangle behave.
No.
Yeah, but
You have an oscillator which in the simplest case would be just a sine wave, right? In the simplest case.
No, but there's another point. So you have a constant baseline, and you are saying that if you have a larger number of sunspots, the rise is also faster. But that is a natural consequence of keeping fixed the baseline.
So with the same growth rate, you could still have a higher maximum.
No, because at the same time for it to
Yeah,
develop,
but
it's always
why the
different.
same
No, but
time?
this correlation
Why
does
the
not
same
exist.
Yes, but
with
that
the
I
decay rate.
understand. But once if you say
Yeah,
that
decay rate
it's
is independent of,
This is not
the,
that triangular example
it
cannot
is-
be given because it does not exist with the decay.
yeah,
rate.
if we find out the correlation with the rise, with the decay rate and the peak value, I mean, we don't have to get much.
But
So
is-
this
I mean,
decay
is
rate
the- is the shape-
is independent.
Is the shape
Yes.
constant? I mean,
Shape means, I mean, there are two different physical phenomena which is governing the rising part and the decaying part.
no, but so the point is this: is there a common envelope to the period? Because if there is a common envelope, you're going back to the same problem over time.
No, the period is also varying, right? The time period of the cycle. is
Actually,
also not fixed. As in, it's not exactly 11
No,
years.
I know, but what I'm talking about is the profile of the cycle. Is there a specific function for the profile of the cycle? Do you get that the decay rate is always slower than the rising rate? Because it looks like
Yes.
more or less they look like very
Yes.
similar in shape.
Yes, that's right.
So the point is that if you have a fixed shape, if you stretch it in one direction, you're going to increase.
I mean, at the moment we don't know what the physics is. I mean, it's not only that there is no physics in it, but we don't even know what the physics is. So you hopefully tell us now.
Yes.
I mean, normally the physics would be that is the sinusoidal oscillator. And then
No,
you
no,
can say there's no
I
physics
agree,
about
but
that. But we don't. But now it's not a.
I'm not sure if
sinusoidal
they are two
oscillator.
independent things or if it's just the same things.
Actually, there is a weak anticoalescence between the period of a cycle and the strain. Like the shorter cycle have a longer period, and the weaker cycle has a longer period, and the stronger cycle have a shorter period. So if a cycle is strong, then the decay rate is almost independent. So if the cycle is stronger, then I mean it has to rise rapidly. So like when I model this thing with the class transfer, then wholly on some physics will be clear from this. Like the stronger, why the cycle is stronger and why there is why I mean when the cycle is shorter. So that time we'll have answer of this. So now we want to model this irregular solar cycle, like the and its features like Monday-Vinio and Wallmeyer effect using dynamo model. So first dynamo model was proposed by Karak in 1955. So according to him, the dynamo model is just basically the oscillation between the polarizal and the toroidal field. Okay, so where the toroidal field is the phi component of the toroidal field, next is case, and polarizal field is the R and theta directed field. So how the toroidal field is generated from colloidal field? So this is known as omega effect. So you know sun has a differential rotation, like it has different rotation in different latitude. So here I show the contour of omega at different theta. You can see that the equator has larger rotation rate than the polar region. Another thing is that near the base of the convection zone, it has a strong radial differential rotation. Okay. So, and due to this differential rotation, the polarizal field gets stretched in the toroidal direction, and it gives strong toroidal field. So, so basically this polarizal field initially is gets stretched in the toroidal direction, and it gives toroidal field due to this differential rotation. And the next one is the polarizal field generation. There are several mechanisms for the polarizal field generation. So the first one is the mean field alpha effect, or the classical alpha effect, again proposed by Karak. So basically, in this case, the toroidal field is twisted by the helical turbulence in the colloidal direction, and it gives small colloidal field, and the diffusion of this colloidal field gives large scale colloidal field. And there is another mechanism for the colloidal field generation. This is known as Bacco-Layton alpha effect, and it is observationally verified. So by this cartoon diagram, I show the I explain Bacco-Layton alpha effect in the following way. So here I show few bipolar sunspot. So basically here by positive sign I show mean that the leading sunspot which are near the equator, whereas this negative, by negative sign we show the trailing sunspot which are near the polar region. One important thing is that the line connecting to bipolar sunspot and the east-west direction has some tilt angle. Some angle, this is called the tilt angle. So, and therefore, when the sunspot decay, most of the flux from the leading polarity goes towards the equator and cancel the flux from the opposite polarity from the opposite hemisphere. Whereas the significant amount of flux from the trailing polarity goes towards the pole and cancel the flux from the old cycle which are there and generates colloidal field for the new cycle. Okay. And in this mechanism, several flux surface mechanism like the strong turbulent diffusion, the meridian circulation, and the differential rotation actually play a major role in this process. Okay. So in this figure, you can see that one polarity flux is going towards the pole, towards the equator, and it cancels the flux from the opposite hemisphere. Okay. Whereas the opposite polarity flux goes towards the pole and it generates dipolar field during the solar minimum, and it's changing sign with the solar cycle. So this observation is verified, and one important thing is that the strength of the solar cycle at the end of a cycle will depend on the tilt angle of the sunspot, bipolar sunspot. It depends on the total magnetic flux from the active region. It depends on meridian circulation and many other factors. Therefore, it involves randomness. Another important thing is that this Bacco-Layton process of generating colloidal field is not self-excited. By self-excited means, I want to say that you know that when the toroidal field exceeds certain value near the base of the conductor, it feels magnetic buoyancy and rise to the surface and gives sunspot eruption, and this sunspot decay and gives the colloidal field. Okay, so if there is no sunspot eruption, then this mechanism will not work. Okay. So like during Monday minimum, so this process is not this important, not that important. There are other mechanisms of the colloidal field generation, like the instability of the toroidal flux tube, which can operate in strong toroidal field region, and like the tachyline alpha effect or other thing. So I'm not talking about this. So now we can develop a flux transport dynamo model. So basically this is the induction equation. Now if we write this total B and the velocity field V as the sum of the large scale field or the mean field and some fluctuating field, and we substitute here, and we can write down the evolution equation for the large scale field or the mean field like this. Okay. Now our approach is kinematic approach, so where the velocity field is given. Okay. So therefore, you don't have to worry about how the velocity field evolve. And in axisymmetry case, we can write the velocity field like this. So this is V phi. It comes from the angular frequency omega, and this V V theta. So these two terms is the meridian circulation, and the magnetic field is the toroidal field and the polarized field. And we substitute this kind of form for the velocity of the magnetic field in the earlier equation, and we can derive this evolution equation for the toroidal field and the for polarized field. So in this equation, you can see that this is a term which is giving the toroidal field from the polarized field by the differential rotation. Okay. Whereas in this equation, this is the source term for the poloidal field from the toroidal field. Okay. So here I show a meridional chart of a solar convection zone. So here this region is the region where strong radial gradient is there, and this is the region where toroidal field is generated. Okay. Whereas this is the region where the poloidal field is generated by the backward-lateral mechanism. Okay. And these two regions are connected each other by several transport mechanisms, and therefore this model is called flux transport dynamo model. And the main transport mechanism for this connecting these two source regions is the turbulent diffusivity. Okay. However, it is not properly understood. It is believed that below the bottom of the convection zone, the turbulent diffusivity is, the value should be smaller because there is no much turbulence. And also it is believed that near the surface, its value is much stronger. We have several indirect evidence from the observation also, and it suggests that the value is of the order 10 to the 12 to 10 to the 13. Okay. However, we do not have much understanding of how this diffusivity vary in the whole convection zone. Therefore, several people use its different value, and it gives two different models. One is high diffusivity model, where value of turbulent diffusivity usually in this range, whereas in low diffusivity model, it is usually in this range. We should mention that the just simple mixing length theory of turbulence, that is 1/3 length scale into velocity scale, uses the value of eta as 10 to the 12 centimeters per second. And the next important agent of flux transport is the meridional circulation, whose value near the surface is observed, and it is around 20 meters per second and is poleward. However, the return flow near the base of the convection zone is not observed so far. However, simple mass conservation principle can allow us to construct the full profile of the meridional circulation, and therefore the dynamo model use mass conservation principle to construct the full profile of the meridional circulation, and this is the typical stream function of the meridional circulation used in flux transport dynamo model. It's the theoretical understanding of the meridional circulation and mainly its fluctuation, like how the meridional circulation vary with the solar cycle and other things, is not studied well. It believes that it comes from the from the combination of buoyancy force, Reynolds stress, latitudinal temperature gradient, and the Coriolis force. Okay. Therefore, we expect that there may be a random variation in the flow due to the fluctuation in any of these driving forces. Okay. However, we have the measurement of the meridional circulation near the surface from 1990s, around 1990s. Therefore, we cannot say anything about how the meridional circulation varied in past with the solar cycle. However, from the study of observed cycle period of last 23 cycles, we can get some idea of the meridional circulation. Okay. And this is because in flux transport dynamo model, the amplitude of the meridional circulation determines the solar cycle period. Okay. Therefore, if we assume that the solar dynamo is flux transport dynamo, then just by fitting the observed period in flux transport dynamo model, we can find out the amplitude of meridional circulation V0. Okay. So therefore, this kind of period variation with the solar cycle can be considered as the meridional circulation variation with solar cycle. So therefore, we can say that that indeed the meridional circulation varied much with solar cycle. We should
9 to 14. So that is period.
This is period. So here I am plotting the period with this cycle number. Okay, and then I am telling that in flux transport dynamo model the cycle period is governed by the amplitude of meridional. This almost inverse. These points are the observed period, value of the observed period, and I am just putting a line neglecting 10% variation. If the variation is 10% each other, then I'm just taking the drawing a line with the average between of the period. Okay. So just to say that how the period varied actually, and then in flux transport dynamo model, the periods observed cycle period is almost inversely related with the cycle with the median circulation. Okay. So therefore, this kind of variation can be considered as the variation of the median circulation. I mean, if the flux transport dynamo.
How
Yeah.
sensitive are the models to this number 0.89? If you
Yeah, that's what I'm telling. Like in Dikpoti Sarman model, it is 0.98. In years Nundi Make, they have found 0.9, 0.885. So it's more or less, I mean, closer. So basically, it's almost just inversely related.
And I think these two models also have different diffusivity.
Different diffusivity, yeah. This model has different diffusivity, and like alpha effect they have considered different way, and mainly there's a diffusivity is the main quantity which is different in these two models. But I mean this dependence almost, I mean, closer. You can see.
Well, which range is that approximately? I mean, most likely this is.
Yeah, the range of V0.
Yes, is it a decade at least in nu, or a decade in variation in nu, over which this law has been established?
not new, right? You mean visible.
V0, this is the strength, I mean, the maximum value.
I mean, it is not natural to have such a broken power law, of course. So one expects that there is a different law. So you have two different time scales. One may have to do with, for example, alpha and omega, for example, and then it could be a certain mean of this and the other one. And then this is just a rough fit. Therefore, I was asking over which range has it been established? Is it an order of magnitude?
Range of velocity, yes, it is around 5 to 40, 50. I think in this case is around 5 to it goes to 50. In this case is much you gave, and I think from
Wonderful.
I mean,
But the period is not even changing by a factor of 2.
No?
If this law is true.
5 to 50 is a factor of 10, so 1 over 10.
no, Pauli in the like. So one thing,
No,
yeah.
10 to the power
10 to the power whatever.
So-
But this is almost 1.
So yeah, Pauli I can show one, yeah.
It's almost 1.
So
0.89 is
yeah,
almost
Pauli,
1.
yeah.
So it's almost a factor of 10.
But the period is changing less than a factor of 2.
No, those are the observed ones.
Yeah, anyway, this should fit.
Yeah, that's
As you claim.
Yes, but maybe their visible is also
No.
changing by small amounts.
Small amounts, right?
Sorry? Then the
Maybe
velocity.
observed
Yeah,
one
that's- yeah.
visible is also changing by small amounts.
yeah. So like this solid line shows the value of V0 required to fit last 23 solar cycle period. So you can see the V0 varied almost something like 12, around 13 to around 30. So this is the V0 required to fit the observed period of last 23 cycle. But the power law, this actually is studied in longer range. Actually. You should also mention that several indirect study from the observed transport data claim that the median circulation varied largely with the solar cycle. So therefore the main sources of irregularities in flux transport dynamo model are the fluctuation in vapor-laden process of generating colloidal field and fluctuation in meridional circulation. Now the fluctuation in vapor-laden process of generating colloidal field is studied in details by this group in both in high diffusivity model and low diffusivity model. And they also claim that observed correlation between the polar field near the solar minimum and the transport number of next cycle is can be explained in high difficulty model. Now, our aim is to study the effect of stochastic fluctuation in meridional circulation in both high difficulty model and low difficulty model. Now, let us understand how what will happen if we introduce fluctuation in meridional circulation in cluster dynamic model. So the physics will come from Yerkes, Nunzi and Mackay work. So this is the evolution equation for the poloidal field, and this is the evolution for toroidal field. So in poloidal field equation, this is the term which is responsible for diffusing poloidal field due to turbulent diffusion. Whereas in this equation, this is the source term for toroidal field.
So what is S?
S is just 1 by r sin theta. S, this one is just 1 by r sin theta. Now,
Where exactly does meridional circulation comes here?
so I'm just here. There is a meridional circulation term, and here. So actually earlier I showed this equation. My important is here the diffusion term in the poloidal field equation, and the source term for the toroidal field equation. I want to explain the fluctuation in meridional circulation. Okay. Now let us assume that the meridional circulation has decreased during a cycle. Okay. Now if the meridional circulation decreases during a cycle,
When you say stochastic effects or random effects, that means that you are changing this particular variables in your equations in a random way, or
when I talk about stochastic, we vary actually randomly. Completely.
Very what?
Yes. We vary randomly.
if you
Yeah, in S, right? Or
No. S is just a constant 1 by r sin theta. When
No,
I'm talking about the fluctuation in meridional circulation, you're talking like.
yes.
Hmm.
So you have a term something like V dot grad over A, right?
V.
Advection term.
Advection term.
Uh-huh.
Then
Yeah.
something
That's
like
right.
V dot grad over A.
Yeah.
And then V is your meridional
Meridional
circulation.
circulation,
And then
there
you change V randomly.
there I introduce fluctuation. I introduce some random.
So V is
So
some constant V plus a fluctuating term.
you can consider.
And this fluctuating, how, I mean,
Well,
what
yeah,
kind of
the-
randomness is it? It's kind of from one snapshot to another, it is completely decorrelated, or
Yeah, this thing can be considered from observation. The thing is, I mean, we have the
choose it from a Gaussian distribution, or
we actually the better thing is we choose I think in our study when I study Wallmeyer effect, we actually use uniformly distributed random number.
and in time, how is it fluctuating?
Yeah, this actually comes from the observation. We have only the observed period of last 23 cycle. So from the observed period, if we again go back to this period, so this is the period you can show. And as I was telling, the period is almost inversely correlated with the meridional circulation. So this plot can be considered as a variation of meridional circulation, and we can see that, I mean, during the earlier cycle, the correlation time of the fluctuation of meridional circulation is shorter, whereas during the recent cycle, the correlation time is, 2-3 cycle. You can see within even like 5 cycle, there is not much variation in meridional circulation.
So you will take exactly this plot and put that in the fluctuation of meridional circulation.
No. When I introduce stochastic fluctuation, we just introduce complete.
So what will make complete? It's constant over one cycle and then changes suddenly.
And then in the next minimum we just change again randomly.
Okay.
Because from this thing we can say we can say like during the earlier cycle it has the correlation time is much shorter, like during every cycle the meridional cycle is varying, and during the recent cycle the variation is not much. So I don't know which one is the typical.
The noise that you put, the correlation time is actually equal to the cycle frequency.
Yeah, yes, that's right. Yeah, and the strength of the fluctuation will actually will be constant by the period variation. I mean, because if we introduce larger fluctuation, the period fluctuation will be also larger. So from the observation, we can find out how much period variation is there, and accordingly we just introduce randomness, introduce the strength of the fluctuation in the. So let us assume that meridional circulation decreases during a cycle. Okay. Now, if the meridional circulation decreases during a cycle, then the colloidal field will remain in the convection zone for longer time. Okay. And therefore, the differential rotation will get more time to induct toroidal field. Okay. And therefore, it will give the stronger cycle.
What do you mean by strong?
Strong means like if the toroidal field is stronger, then the cycle, then the transport action will be
Long or short?
stronger. Means that the strength of the cycle is stronger. Means
Even there will be more number of
transport.
Okay.
So
Yeah.
if the meridional circulation is decreases in this cycle, in the next cycle,
Next cycle will be stronger. Yeah, because the meridional circulation weaker means the colloidal field will remain in the convection zone for longer time. Therefore, the CR will get more time to induct toroidal field. Because the colloidal field will remain for longer time in the CR layer. Therefore, it will generate more toroidal field, and therefore the next cycle will be stronger. Okay. On the other hand, on the other hand, there is another effect. If the meridional circulation is weaker, then the colloidal field will actually get more time to diffuse in the convection zone. Okay. If it remains for longer time, then the colloidal field diffusion will be also more, and therefore ultimately it will give very weak toroidal field, and the cycle will be weaker. Okay. Now, whether this effect, whether this effect is more important or this will depend on which of these two, if competing effect we know what. Now, in low diffusivity model, the diffusion is not much important, and therefore this effect is not important, and therefore weaker meridional circulation means stronger cycle. Okay. On the other hand, in high diffusivity model, this effect is more important, and therefore the cycle will be weaker. Okay. So therefore, in low diffusivity model, weaker meridional circulation means stronger cycle, and high diffusivity model, weaker meridional circulation means weaker cycle.
yours is actually a high diffusivity.
Yeah.
And
Actually-
motion is actually a low diffusivity.
Yeah, actually I have I have done all the calculation in both the model, and we have find out what is the difference. So this is the physics actually. So with this understanding, we first model the last 23 solar cycle period using variable meridional circulation. Okay. So this is the result. So this solid line shows the value of V0, the amplitude of meridional circulation, used to model last 23 solar cycle period. Okay. And this is the sunspot number. So dash one is the theoretical sunspot number, and the solid one is the observed sunspot number. Okay.
So when you say used to model, how exactly is this done?
Yeah. So basically, we just first the code is running in a relaxed mode. Oscillator is giving oscillator solution, and we stop near the solar minimum, and we vary the meridional circulation to match the period of the next cycle. So basically, this we have some indication from the earlier that the meridional circulation is almost inversely correlated with the period. So we can get some idea what will be the, I mean, if this is the period, then how much will be the value of the meridional circulation.
So at the beginning of each period,
Like-
you actually choose a meridional circulation.
Like we stop the stop code here,
Yes.
okay, and we can find out. Let's say this is 11 year, and
Right.
if this is 11 years, then how much will be the period? How much will be the V0? And then we actually put the value of V0 up to the next of the next minimum, and again we change V0 to match the period of this one. Okay, so we do not try to fit exactly the period. I mean, but we fit it.
And then when you
Roughly.
get this plot, how does the upper plot?
Yeah, rough.
How does that match with the variation of meridional circulation that you know from observations?
No, from the observation we don't have meridional circulation. So this is the one goal, like how the meridional circulation varied.
But
In observation we have only the solar cycle period.
But we also know the meridian circulation at least for last cycle, right?
For one cycle I have, yeah, from 1990s around, yeah.
And how does that compare?
Yeah, actually, during the earlier cycle, I do not remember how much was the, but during the recent cycle, there is actually indication the meridian circulation is weaker. And during the earlier cycle, it is around 30 meters per second. So, interestingly, you can see from this figure that the most of the theoretical transport number is matched with the observed one. Okay. Observed one is shown by solid line. Okay. So therefore, this is an interesting result because my goal was to model the solar cycle period. Okay, by using variable meridian circulation. Okay. However, we see that the most of the cycle amplitude also match. Therefore, we get a significant correlation between the peak theoretical transport number and the peak observed transport number. Okay. So, therefore, these studies says that the meridian circulation not only determine the solar cycle period, but also model the solar cycle amplitude also. I mean, up to some extent, it has some effect on the solar cycle strength also.
What do you mean by R equal to 0.75 and 9.9%?
I mean, this is the significance level, or and the R is the linear correlation. I mean, how these two quantities linearly correlated. So next we repeat the same study in low DPC model based on Dikpotian Sarvani 99 model. Okay. So this is the result. So we can see that the theoretical transport number and the observed transport number is not matching each other. So therefore we do not get any significant correlation between the peak theoretical transport number and peak observed transport number. Next we study Wallmeyer effect. So as I mentioned that the stochastic fluctuation in the colloidal source term and in meridional circulation are the two main sources of irregularities in flux transfer diagram model. Therefore, to study Wallmeyer effect, first we introduce stochastic fluctuation in colloidal field source term. Okay. And this is the result of WE1. So let me again remind you that WE1 is the anti-correlation between the rise time and the peak transport number. Okay. However, here instead of anti-correlation, we are getting a weak positive correlation between the rise time and the peak transport number, both for high DPC model and for low DPC model also. Okay. Therefore, this study cannot explain WE1. However, the WE2, that is the positive correlation between the rise rate and the peak transport number, is reproduced here. So we can see we are getting a significant correlation between the rise rate and the peak transport number, both for high DPC model and in low DPC model. Therefore, this study explains WE2. Now we introduce stochastic fluctuation in meridional circulation. So by stochastic fluctuation in meridional circulation, as I was telling earlier, we just during every solar minimum we just change the meridional circulation randomly. So this is the result of WE1. So you can see that in high DPC model we are getting a significant negative correlation between the rise time and the peak transport number. Therefore, this study explained WE2. Whereas in low DPC model, still we are getting positive correlation. And WE2 is reproduced as earlier. Okay. So, from this study, one important thing is that the meridional circulation, stochastic fluctuation in meridional circulation is required to explain WE1. Now we introduce stochastic fluctuation in both. I mean, that is what expected in reality. So stochastic fluctuation in colloidal source term and stochastic fluctuation in meridional circulation. So these are the results. So you can see that the high DPC model WE1 and WE2 both are reproduced. Whereas in low DPC model WE1 and WE2 WE2 is reproduced, WE1 is not reproduced. Therefore, fluctuation in medium circulation is required to explain Waldmeier effect, and only high diffusivity model is able to explain Waldmeier effect. And one important thing is from this figure you can see that the scatter is less in high diffusivity model, okay. And that is because the diffusivity is much larger in the high diffusivity model, and therefore any fluctuation introduced in high diffusivity model will be washed out within few years. And therefore, the scatter is much okay. So we have understood that meridional circulation is important in modeling many regular features of solar cycle, and therefore we ask the question: can a large fluctuation in meridional circulation produce a Mondale-like grand minimum? So to answer this question, we propose that during the beginning of Mondale minimum, the amplitude of meridional circulation dropped to a very low value, and after a few years it again increased slowly. Okay. So this is our assumption. Whether there is any physical justification or not is a different thing, but this is our assumption that the beginning of Mondale minimum, meridional circulation decreased to a very low value, and then again it slowly increased. So with this simple assumption, we are able to reproduce Mondale-like minimum remarkably well. So this is theoretical butterfly diagram of theoretical sunspot number. So we can see that the north-south asymmetry, which was observed in the observed sunspot butterfly diagram, is reproduced in this plot. Okay. It also reproduces the observed sudden initiation of the Mondale minimum and the gradual recovery. Okay.
Can you go back one slide? So when you say large fluctuation, you mean large decrease.
Large, I mean here it is a decrease.
Okay. And from the model, is it clear why it starts in the southern hemisphere?
Why this asymmetry?
Yeah.
Yeah. Actually, in this model, I mean, to reproduce this kind of model, we know that there is asymmetry in the observation. Okay, and therefore we actually assume we introduce asymmetry in the meridional circulation, like.
So the model doesn't explain it, it's put by hand.
It's put by hand because we know there is asymmetry, and it is actually observation also says that there is asymmetry in meridional. So solid one is the southern, okay, and the dash one is the southern, and the solid one is the northern. Yeah. So this solid one actually is, rising faster, okay, and therefore actually the sunspot eruption also started. Yeah. So this is just assumption. I'm just telling that let's decrease the meridional circulation. However, with this simple assumption, it reproduces the several features of Mondale minimum remarkably well.
So what happens to the strength of the dipole?
What happened to the
Strength of the dipole?
strength of the dipole?
Yes. The global field of the sun.
Strength of the radial field or the polar field near the solar minimum. Yeah, actually we have shown. Actually, if we reduce this meridional circulation to a very low value, then the the dipolar field also actually reduce. Okay.
So
Strength of the dipolar field actually reduce, and therefore the toroidal field is also reduced, and the it stop the sunspot eruption.
So the question is, can you get the drop in sunspot number and the modulation in the radioactive tracer on Earth at the same time, or does reducing the sunspot also wipe out the modulation?
Yeah, modulation in the
C14 or the very
Yeah. I have reproduced this also. Yeah. So that's why I'm telling that it reproduces many things. So this is one thing, and the next one is that as mentioning the solar cycle was going on during the Mondale minimum, as suggested from beryllium 10 data and carbon 14 data. Okay. So and this figure actually shows this actually explain that oscillation. So to reproduce this figure, we calculated the radial field in the solar wind. Okay. Because the radial field in the solar wind actually is responsible for giving the oscillation in the cosmogenic data. Because
You don't have a solar wind.
sorry?
You don't
I
have
mean-
a wind in your
Just
sun.
measuring
No,
the
I'm just
radial
measuring
field.
this because
So radial field is certain.
if the strength, this radial field is stronger, then the production of this cosmogenic isotope will be weaker. Okay. Because cosmic ray will not able to come to the towards the earth, and then the production of this cosmogenic isotope will be weaker. Okay, so therefore this radial variation of this radial field in the solar wind actually should corresponds to the oscillation in the in cosmogenic isotope data. Okay. So therefore it shows this oscillation. So you can see that the strength is weaker, is normalized to 1. You can see the strength is weaker during the Monday minimum, and however there is oscillation over there. And another important
This is observation, right?
no, this is from our model. Yeah, this is just we calculated the radial field from the solar wind. Okay, in
What
observation
height in the model?
around three solar radius from the surface. Yeah. So another thing.
So how do you assume the field decays outside the sun?
How do you assume the?
When your model is just a model of the sun, right?
Yeah, model of the
Now
sun.
you take the field that swings solar radius
Yeah, actually,
outside the
yeah.
sun.
So actually, above the surface, the field is potential field. Okay. So del cross B equal to 0, and
So
then
you
says
extend it like a potential.
yeah. And then we find out certain areas where the field is completely radial. Okay.
There is a solar wind correction actually, which is in there. That Moushumi also uses, and I think she first started using that solar wind correction from a certain reference. Now I don't remember what the reference is. So that correction is used for the potential field extrapolation. It's not pure potential in that sense.
Yeah. Another important thing is that that Miyaha et al. Reported that the solar cycle period was longer during Monday minimum, and this is also reproduced in this plot. You can see that the period is longer than 11 years, and this because the meridional circulation is weaker during Monday minimum. That was our assumption. Okay, so we explain this thing. Now, as he was explaining, he was telling that that was the colloidal field or the radial field or the dipolar field during the solar minimum was also weaker, and the answer is yes. Actually, earlier we have shown that if we reduce the colloidal field during the minimum of a cycle, and then we can able to reproduce model-like minimum. If we just cut the colloidal field to a very low value, and we run the model for several cycles, and then we are able to reproduce the model-like minimum. Okay. However, in both the cases, earlier we saw that the meridional circulus had to reduce to a very low value, or we have to reduce the colloidal field to a very low value. But we expect that there may be a fluctuation in both process. So, if we reduce the colloidal field to a little bit, then at a moderate value of meridional circulation, we are able to reproduce model-like minimum. So here I show that the value of meridional circulation and the colloidal field reduction factor, okay, which can give model-like minimum. Okay. Now I will talk a little bit about the memory of solar cycle. So as I mentioned that this is the region of toroidal field generation, and this is the region of colloidal field generation in flux transport dynamic model. And these two processes are connected by each other by several transport mechanisms. Okay. And therefore, the memory of the solar cycle will depend on the mechanism of the flux transport, how the colloidal field is coming to the toroidal field. And it is believed that this colloidal field actually gives the toroidal field, and this toroidal field is a measure of transport number. Okay, and this thing actually already is studied in details by these two groups, and they says that there is a strong correlation of the radial field of cycle n and the toroidal field of cycle n plus 1. Okay, and this also found in observed data from the last 3 cycle polar field data, and there is a correlation. And now the question is, how long is the memory? I mean, is it one cycle? That means the toroidal field of cycle n will be determined by the colloidal field of cycle n minus 1 only, or it is many cycles. That means the toroidal field of cycle n will be determined by the polar field of cycle n minus 1, n minus 2, n minus 3. Okay. So this question was answered again by these two groups, and this they are telling that the dynamo can operate in two different regimes. One is diffusion dominated regime and another is advection dominated regime. In diffusion dominated regime, the diffusion is more important in transporting the field, and therefore the polar field of cycle n will only correlate strongly with cycle n plus, or toroidal field of cycle n plus 1. Okay. There will be no other correlation. However, in advection dominated regime, the diffusivity is much weaker, and therefore the polar field of cycle n will be correlated with the toroidal field of cycle n plus 1, the n plus 2, n plus 3, and so on. Now, we have shown that in whichever regime the dynamo is working, whether it is diffusion dominated or advection dominated regime, the solar cycle memory will be always one cycle, and this is because in both the model, this important mechanism of transporting field is turbulent pumping, which is not included. Okay. So, and this is unavoidable in mean field equation. So this is the equation for the mean field. So we can see that there is a term E, which is actually given by this. So if we substitute this term, this expression here, we can see that there is a term gamma which acts as an advective term in this equation, and this is known as the turbulent pumping. Okay. This acts like a advective term in the wind flow.
I have a stupid question.
Yeah.
How is it possible that a cycle can correlate with the previous one,
Yeah.
but not with two cycles behind? If each cycle correlates with the previous one, then
Yeah.
each cycle should correlate also with 2 behind, 3 behind, 4 behind.
Yeah, actually,
It's kind of like, how long is your memory?
yeah. So yeah, this
You're saying that the cycle is kind of Markovian with one cycle back.
yeah. So you can look at these two,
I
like
mean, how,
Yeah.
go back, how good is the correlation
Yeah.
on the first two? I mean, if
yeah.
so, it was 100% correlation, it would be 100% correlation for the cycle, right?
No, no.
It's basically an exponential, right? So the exponential is falling off at a certain time. This could be either one cycle, it could be two cycles. And of course, if it's
Yes, but the point is that if you have a very high correlation in one cycle, I don't see how can you wipe it out completely.
but you don't have a very high. It's 1 or whatever.
No, this thing will be like in the if it is in high diffusivity model, the diffusion is much stronger.
No, but
Let's say
yeah, but my point has nothing to do with
Okay.
diffusion. It's just with how you propagate correlation.
yeah, yeah.
I mean, you can go back to
Yeah.
the slides where you were showing.
Yes.
No,
Okay.
the one where you were
Yeah,
comparing
yeah.
the two models, the
Yeah,
attraction.
this thing. Yeah.
Yes. So,
Yeah,
so I don't see much difference between
actually
the n plus 1 cycle on the diffusion dominated and the advection dominated regime. They look pretty much similar in terms of how correlated they are. These
no this
and the other one.
This,
yes,
yeah.
they look pretty similar.
yeah, n to n plus correlation is always there.
Yes, so I don't understand how then one decays completely down.
No, the question is whether this correlation, that is the n to n plus 2 or n to n plus 3 and other this correlation will be there or
So,
not. Okay.
so if you convolve n plus 1 twice, you should get n plus 2. Right?
But there is no correlation if you compare these models.
No, but if you take this as a point and you claim there is a correlation, if you convolve n plus 1 twice with itself, you get n plus 2.
X-axis and the y-axis are different parameters of the cycle.
No,
No,
they
this
don't
X,
look like-
X-axis are same. Yeah, all the axes are same.
No.
Yeah.
X and y.
X and
One
Y.
is radial and one is toroidal.
Radial is toroidal, yeah.
No, but what I'm saying is that, yeah, probably they're not exactly the same. So I was wondering,
I see what you're saying. You're thinking that this disclaimer auto correlation is a function of time.
yes,
Yeah.
Yes, but may not be that, right? It is toroidal to colloidal radial, and again toroidal n plus 2 to radial n.
So you're comparing a different.
Even actually, if you compare in the same cycle, the correlation is pretty low. It's only cycle and 1 plus where the correlation is relatively high.
What do we have left in dominant increasing?
Yes, I was just looking at the left. I
Mm.
didn't look at the
There's
right.
a strong correlation. in
That
the
is
center.
true, yes.
Mm.
So basically, just if you just plot
No, okay. I see the point.
like for high diffusivity model, let's say this one, it will just fall sharply.
But then it's not a question of memory at all, right? It's only a question of the first slides, how the radial and the toroidal correlate in the cycle.
In the cycle, it's not well correlated.
On one side and on the other is well correlated,
Yes,
right?
yes, right.
So the difference in the memory is actually only due to that.
Due to the first sliding each other,
Yes.
each other's series.
So the difference between these
Yes.
two has nothing to do with the memory, nothing to do with the first slide, which is based on time point. I don't see how this has anything to do with memory.
Memory.
I mean, you're
in the
telling-
sense that how strongly or how well is the colloidal field of the previous to previous cycle
No,
is
but-
preserved in the sun.
So the reason why from
That's it.
from the B slides you go to the C, in one case there's no correlation, and the other case some correlation remains,
Yeah.
is because of how the points are distributed on slice A. That's the only reason.
The difference between the two you mean.
Yes, the difference between the advection, the diffusion dominated, the advection dominated is only because of how A is, not because of
No,
how B
actually,
is.
in
And if it depends only on A, which is the instantaneous phase, this has nothing to do with the memory.
actually this correlation is coming. This is due to different region, and this is actually the following. Yeah, I understand your point. So actually in reality, I mean real sun, the field, this colloidal field near the surface, this comes to the base of the convection unit by two mechanisms, like meridional circulation and the diffusion, turbulent diffusion. And then toroidal field is generated here, and then it's due to negative buoyancy, it's rise to the surface and gives transport eruption. But in this model, the meridional circulation is there all the way. Okay, so the some toroidal field actually is coming. I mean, the meridional circulation is taking some toroidal field to the surface. Okay, so therefore some toroidal field is directly coming towards to the surface, and therefore this end-to-end correlation is exists. And in the advection dominant region, what I have shown, actually their meridional circulation is much stronger and the diffusivity is weaker. And in the diffusion dominant region, meridional circulation is weaker, diffusivity is stronger. Okay. So actually, therefore, this end-to-end correlation, this thing is coming due to this because the meridional circulation is taking some toroidal field is, to the surface, and therefore this end-to-end correlation is there. Okay. Because the meridional circulation is unavoidable and this completing this thing. But in ideally the toroidal field should actually, when it exceeds some value, it rise due to the magnetic buoyancy and it gives transport eruption. Okay. I mean this is the actual process how the toroidal field is coming to the surface. Okay. But in this flux transport dynamo model, actually some part of the toroidal field is coming by the advection. Okay. This is not the actual, actually happening in the sun. Okay. And to reproduce this thing, they actually these two plot is taken from Nondi and Meke. So they are not using extremely high, strongly diffusion dominant region and the strongly advection dominant region. They actually change some parameter and then they have shown that okay, with this parameter they are telling this can be considered as high diffusivity model and this can be considered as advection. So I mean the point is in advection dominant region the toroidal field, strength of toroidal field is determined by the not only the colloidal field of n-1 but also colloidal field of n-2, n-3 and that. Yeah. So yeah, this is so So to give the idea of the importance of turbulent pumping in flux transfer dynamo model, we can calculate the time scale of this flux transfer mechanism, and let us calculate the time scale of the advection by Maidon circulation, and it is around 10 years if we use 20 meter per second Maidon circulation. And the time scale for the turbulent diffusion is 2.8 years if we use ETI equal to 5 into 10 to the 12 centimeters per second, and it is 276 years if it is 5 into 10 to the 10 centimeters per second. So therefore, if it is in high diffusion level region, this memory is shorter, whereas in low diffusive model the memory is longer. Okay. However, the time scale for the turbulent pumping is 3.3 years if we even use the turbulent pumping speed as 2 meter per second, the radial pumping speed.
How do you get that?
This actually, the numerical simulation suggests that there is the few meter per second turbulent pumping speed is unavoidable. The radial pumping speed. This Kapila et al. The axle is also one corner.
Does the
So-
estimate
So even they are telling that even like pipes.
I think probably they do because some of those pumping profiles are also used by Gustav.
Gustavo was in flux transfer dynamo model, and
So how does one estimate the pumping velocity?
basically
Just dimensionally?
Have the negative gradient of eta t times a half is one possibility, but the tau might not be inside, might be outside.
some people suggest tell that.
So this will depend upon the eta t profile that is chosen?
Yeah.
Okay.
So that actually does go upwards, unless one relies on u, which goes downwards.
So to calculate this
And
pumping
the tau
time, you have
also
taken the
not-
thickness of the tachocline? Or
No. By this, when I am calculating this time, this thickness, the thickness of the 0.3 r, like from surface to the how the polar phase is coming from the surface to the base of the convection. So this thickness divided by pumping speed. Yeah. So if you include this radial pumping in the flux transport dynamo model, then we see that even in advection dominated regime also the other correlation that is the n2n plus 2 correlation, n2n plus 3 correlation is destroyed. We have only a strong correlation with n2n plus 1.
But the turbulent pumping should not be there in the entire convection zone, right? It should only be there in the transition region.
No, yeah, everywhere. Why not?
Below the convection zone it is,
What if it's gradient of eta t or whatever? Then it's
In any case, it's always everywhere. But
gradient of eta t will not be everywhere, right?
I mean, it's not constant everywhere.
Yeah,
It's
that's
only
what I'm
constant if
saying.
you
It will
assume
be
it to be
larger
constant.
only near the base of the
So
convection.
either T and the sun has a profile in the mixing link theory which looks like
this actually
looks
is
like
basically that
something like this.
tar-
There's at 0.8.
So it's
But
shortest
that's not the-
actually in the.
But that's not the eta t that is chosen by you.
No.
No. This is not. This will be.
So
only
here your
the-
lambda is independent of the eta t in your model, or
Yeah.
lambda is not
Not-
grade minus gradient?
Yeah. In this model, like I was telling that we just use very simplified constant beta. So you see that the memory of solar cycle is always one cycle. It's independent of the region where the dynamo is working. Okay. That's all.
Yeah, thank you. Questions, please. There was one question from Niccolo who asked what does the strength of the cycle actually mean. So what does it actually mean regarding toroidal and toroidal fields. Are the toroidal and toroidal fields always equally strong in each? I mean, are they correlated, or is there a stronger modulation of toroidal rather than toroidal field? I mean, the toroidal field is normally what you think it makes a sunspot number, right?
Yeah, yeah.
And how does the toroidal field correlate with the toroidal field?
Yeah, the toroidal field is correlated with the colloidal field. Yeah, because the colloidal field is actually coming from the, giving the toroidal field. So that's what, yeah. So this colloidal field, if the diffusion is weaker, then the colloidal field will be advected towards the pole, and then it's coming to the base of the convection zone. And the toroidal field is generating near the high latitude because there is a stronger latitudinal gradient. So, and then again it's is advected towards the equator and gives sunspot eruption. Okay. And so if the diffusivity is stronger, then the significant part of the colloidal field will directly come to the base of the convection zone directly. And so this meridional circulation path will be short-circuited if the diffusivity is much stronger. Okay, and therefore in the high diffusive mode we are getting one cycle correlation. Like the colloidal field will directly come to the base of the convection, and therefore and then it will give toroidal field, and then it will give sunspot reaction. So by strength of the sunspot cycle basically means that the strength of the toroidal field. So the good measure of the toroidal sunspot number, maybe the volume integrated toroidal energy of the toroidal field. Yeah. So this correlation is, theoretically, from this flux sunspot dynamo model, there is a strong correlation. And Chaudhary and other, from the observed 3-cycle polar field data, they found a strong correlation. But we have only the polar field data of 3 cycles. Okay. So this is the correlation from the observation.
I'm slightly confused, maybe I understood it wrong. So you are saying that a toroidal field of this cycle is strongly correlated with the colloidal field of the next cycle. Previous cycle, right?
Yeah.
But when you change the meridional circulation by a significant amount, then essentially your toroidal field shuts down in the Mount Avenue.
Yeah.
Right? But your colloidal field still goes through a cycle. So then there is no correlation between the toroidal and colloidal.
No. There is a correlation, but the colloidal field, all the fields are there. Fields are oscillating, but the fields are weaker. Toroidal field is weaker. That means it does not, for giving a sunspot eruption, toroidal field has to exceed certain value, and it's of Galois always 10 to the 5 value. So the toroidal field is during the Monday minimum is not exceeding that value. Okay, but it is varying cyclically, but it's not exceeding the critical limit where it can give sunspot eruption. Okay.
But how much is this critical limit? Half of the. If I take your plot where you show that the colloidal field is only half, right? I would assume that the toroidal field is only half if the correlation has to be preserved of some sort. So that would mean that the threshold for sunspot formation should be about half of what we have now.
What does that?
But the colloidal field is never quantum sunspots.
No, but if you say that they're both correlated, right? So if the colloidal field goes down by factor 2, the toroidal field goes down by factor 2.
Is this really true in the simulations? So we have seen that the radial field goes down by something like a factor 2.
Yeah.
Is it true that the toroidal field does go down by about the same value, or is it different? What does the simulation say in this respect?
Yeah. See, I do not have this. Yeah, I have shown this thing. No, probably. I had yeah, I have actually shown that the value of the toroidal field, also how is the value actually decreased, but I have not put in its value actually decreased to the limit where it can give the sunspot eruption.
Yeah, but is the reduction in the toroidal?
The reduction is in the toroidal fields around around 40% is a reaction.
Yeah, so that's the same.
Yeah. I don't remember, but I have got in the paper. But
It's a very shallow pressure, right?